another example problem. This time it is example 2.2. Two charges, 3 into 10 power minus 8 coulomb and minus 2 into 10 power minus 8 coulomb are located 15 centimeter apart. At what point on the line joining the two charges is the electric potential 0? Take the potential at infinity to be 0. So that is the last sentence. Take the potential at infinity to be 0 is common, okay? Because only when you take the potential at infinity to be 0, then you will get this equation kq by r. We saw that, right? Otherwise, it's r1 minus r2 is what you're going to get. If r2 is at infinity, then that part, the second term, becomes 0. So we consider the potential at infinity to be 0, and once it is 0, then the potential at some distance from the charge is just kq by r. So that is understandable. That is what is reiterated in the problem. We'll do it. So it's example 2.2. So example 2.2. So two charges, 3 into 10 power minus 8 coulomb and minus 2 into 10 power minus 8 coulomb are located 15 centimeter apart. So I have this one Q and then this is okay. So this is 3 into 10 to the power minus 8 coulomb, and this is minus 2 10 to the power minus 8 coulomb. Okay, and this distance between those two charges is actually 15 centimeters. 15 into 10 to the power minus 2 meters. Okay, so that's the distance. So they want they want you to find the points where the potential will be 0 due to these charges. So what did we figure out? Potential at any point is going to be equal to the algebraic sum of the potentials due to all the charges in the system, right? Okay. So now let's think where you could have a 0 here. Well, the potential due to this would be negative. Why? It's kq by r. Q is a negative charge, so minus 2. So you're going to have a negative potential due to this charge. Why? Because this is negative charge and my test charge is going to be unit positive test charge, so that's going to be attracted by it. When it is attracted by it, what kind of force will what kind of work will I do? Suppose, let's think about it for a second. So there is this negative charge and then there is this unit positive test charge that you are bringing. It's going to get attracted. Okay, what should you do? You should do work against this conservative field. What does the field try to do? It tries to attract it already. So when you bring it from infinity to this point, even if you don't do anything, this is going to come there. But then what's the condition? It should reach that position without any change in the kinetic energy. So what should you do? You have to apply brakes now. Okay? So the charge will try to, the unit positive charge will try to go there, and then you need to hold it back. So you are going to do this braking motion. Okay? You are going to apply a braking force now. So your force is in the opposite direction to the electrostatic force, but the body is moving in the direction. So in that case, the electrostatic force does positive work and you are going to do negative work because you are applying brakes, notice. You don't want it to accelerate. Okay? So that is how we have defined potential energy. Okay. So if you have a negative charge, because your other charge is unit positive test charge, it is going to be attracted. Even if you don't do anything, it will go to that place from infinity. So in this case, you need to restrain it from accelerating. So you are going to apply brakes on it. You will pull it back this way. The body is moving in the direction, but you are trying to pull it back this way. So you will be doing negative work there. Okay. So the potential due to this will be negative. And that's how you see it. Negative charge, potential due to negative charge will be negative. Okay. So this is going to have negative potential around itself, and this is going to have positive potential around itself. So at some point, this potential and that potential can be equal and cancel. That can happen here once, right? It's going to happen here once. So if I take this point, okay, I take this as the origin, okay, with my reference origin, and this is the point, A is the point here. At some point here, the potential due to this and the potential due to this will cancel each other. Why? Potential due to this will be positive, and potential due to this will be negative. So it's possible that they cancel each other out. So what is VA? So VA is equal to VA due to the positive charge plus VA due to the negative charge. So that must be equal to 0. Okay. So what do you get here? Suppose this distance at which it happens is x. Okay. What is the potential due to A? Potential at A due to this positive charge? Well, VA plus is going to be equal to K Q by R, right? So K, that is 9 into 10 power 9 K. What is Q? Q is 3 to 10 power minus 8. So divided by what is R? R is X. That is the R. Okay. Then what is VA minus? Potential at A due to negative charge. And that is going to be equal to say 9 to 10 to the power 9 into, now you got minus 2 10 power minus 8 by, what is this distance? Well, this is 15 centimeters and this is x centimeters, let's say, and this must be 15 minus x. Okay? So 15 minus x. Okay, so let's say this is x centimeters, right? So I'll say x into 10 power minus 2 and I'll say 10 power minus 2. So in this case, I'm going to take x as x in terms of centimeters now. Okay, so this is what I get. So when I add these two, VA is equal to 9 into 10 power 9 into 3 into 10 power minus 8 by x into 10 power minus 2, then add plus minus 2 into 10 power minus 8 into 9 into 10 power 9, so divided by 15 minus x into 10 power minus 2. So this will become negative, right? So I'll say this is negative. And this must be equal to 0. So we should cancel each other out. Right? So the potential due to this must be equal to this one. So when I get something like this, then I can take it to the other side, right? So because 9 into 10 power 9 into 3 into 10 power minus 8 by x into 10 power minus 2 is equal to 2 into 10 power minus 8 to 9 into 10 power 9 divided by 15 minus x to 10 power minus 2. Okay. So I can start cancelling stuff. 9 will go, 10 power 9 will go, and 10 power minus 2, 10 power minus 2 will go, and then 10 power minus 8, 10 power minus 8 will go. So I will be left with 3 by x is equal to 2 by 15 minus x. I just need to solve this problem. Alright, bring it here. So 45 minus 3x is equal to 2x. So it goes there, 45 is equal to 5x. So x must be equal to 45 by 5, 9 centimeters. So from here, so 9 centimeters from the positive charge you will have a point where the potential is actually 0. That is, potential due to this and potential due to this will cancel each other out. That is one point. And it is also possible, that this side you can have another point where this value and this value can cancel each other out. Okay? You can have a point here also, this side. If I extend it, there can be a point here. I'll call it as B. So potential due to this, potential due to this at this point can cancel each other out. But can I have such a point on this side? I cannot have it. Why? Because you see, this distance is shorter for the positive point, well, positive charge, but the positive charge is greater. So the negative charge is smaller and then the distance is also farther. So on this side they can never cancel. But on this side, notice here, the negative charge is smaller than the positive charge, alright. This is 2 and this is my 3. But then I can have a shorter distance for the negative charge. And that combination can cancel this bigger charge at a longer distance. Okay. So I can have another point here where the potential due to the positive charge and the potential due to the negative charge can cancel. But I can't do the same thing this side. That cannot happen. Well, this is already greater than that one and it is closer to this point. So the potential due to this will be greater all the time. So it can never be cancelled by this one. Because it is farther, it is smaller and farther. So that can't happen here, but it can happen on this side. Okay. So let's try to do this. Okay. Let's say this distance. This distance is y. Okay, that is y distance. Now, again, what is the potential B? VB is equal to VB due to the positive charge plus VB due to the negative charge. And that must be equal to 0 totally. Okay, so what is VB plus? I'll do it here. So VB plus is going to be, so VB plus is going to be 9 into 10 power 9 into 3 10 power minus 8 by, this is 15 centimeters plus y, 15 plus y into 10 power minus 2. Okay, and then what is VB minus? VB minus is equal to, say, 9 into 10 power 9 into minus 2 into 10 power minus 8, so divided by simply y. Okay, so y into 10 power minus 2 meters. This is potential. So I just need to add them, right? So when I add them up, VB is equal to 9 into 10 power 9 into 3 into 10 power minus 8, so divided by 15 plus y into 10 power minus 2, then minus 9 into 10 power 9, because I have minus here. So I will do 2 into 10 power minus 8 divided by y into 10 power minus 2. Y in centimeters now. So this must be equal to 0. So that gives you, so this must be equal to 0. So that gives you 9 into 10 power 9, so 3 into 10 power minus 8 divided by 15 plus y to 10 power minus 2 equaling 9 to to 10 power 9 into 2 into 10 power minus 8 by y to 10 power minus 2. So clearly 9 and 9 will cancel, 10 power 9, 10 power 9 will cancel, 10 power minus 8, 10 power minus 8 will cancel, 10 power minus 2, 10 power minus 2 will cancel. So now I have another equation, 3 by 15 plus y equals 2 by y. So this gives me 3y equals 30 plus 2y. Okay, so if I bring it here, then y is equal to 30 centimeters. So y is equal to 30 centimeters. Then this point B is 30 centimeters from the negative position. From the positive, it will be 15 plus 30. So 45. So B is, okay, B is 45 centimeter from the positive charge. Okay. And A is 9 centimeter from the positive charge. So this is how you do this problem. Let's do example problem 2.3. Let me read out the problem and then we'll start doing it. The problem is this. The figures, there are two figures A and B, show the field lines of a positive and a negative point charge respectively. Okay? So there is this positive charge and there is a negative charge. And there are 2 points mentioned here, P and Q, and then here A and B given there. Now the question is this. Give the signs of the potential difference Vp minus Vq and also Vb minus Va. Okay. First of all, let's take a look at this. You see this is a point charge, the positive charge, so the field lines go away from it. Because if I take a unit positive test charge, that will be repelled by this. So you are going to draw lines in the direction of the movement of the unit positive test charge here. Then you have negative charge here. Again, you are going to bring unit positive test charge, but that will be attracted towards the negative charge. So the field lines go into the charge here. Again, there are two positions A and B given in this. Now, what is the question? The first question is, give the signs of the potential difference Vp minus Vq and Vb minus Va. Let's take this. This is Vp, this potential is Vp, and then this potential is Vq. So they want you to find Vp minus Vq. What would this be? Okay. What's the sign of this actually? Look at this. This is closer, right? P is closer to the charge than Q is. So what do we know? The potential is actually for a point charge at any point is given by K Q by R. So Vp must be greater than Vq. Why? Because R is smaller for P than it is for Q. So Vp must be a greater number and then Vq must be smaller number because it's farther from the charge. So this Vp minus Vq should give you a positive number. So the potential difference between P and Q must be positive. Vp must be greater than Vq because it is closer to this. So R is smaller. So Vp will be greater than Vq. Likewise, the second part is, what is Vb minus Va? Let's say this Vp minus Vq. What is Vb minus Va? Okay. So here, the negative charge, and what do you think this is going to be? So this is actually it is farther from the negative charge. Okay, but then the field value will be negative. VB will be a negative potential. Why? Because what is VB? VB is equal to K into Q. In this case, Q is minus Q, because you have a negative charge there. So you will have a negative potential, minus Q by R. So that's the V as far as this is concerned. You take any point, the potential at that point is given to minus KQ by R because you have a negative charge there. Here it is KQ by R because you have a positive charge here. So this is minus KQ by R. So you see, this is this distance R, V, let's say, I'll do it here. Okay, VA is going to be equal to minus KQ by, let's say this is RA. This is RA. Okay, and then VB is minus KQ by RB. From here to this RB. So clearly RB is greater than RA. So RA will have a bigger magnitude. KQ by RA will be a bigger number, but then we have a negative there. So this could be, this is actually smaller than this. Why? Because this is a smaller negative number, but this is a bigger negative number. So because of that, this you are going from here a smaller negative number to a bigger negative number. This is a bigger negative number. So what would happen to VB minus VA? This is smaller negative number minus of a bigger negative number. So the bigger negative number will become positive, and VB is negative. So you will get again a positive number here. So VB minus VA is going to be positive number here. So that's a sign. So the potential difference between VP and VQ, to go from VP to VQ, that is positive. Here, from VB to VA, that's going to be positive again. So that is how you answer the first question. What is the second question? Give the sign of the potential energy difference of a small negative charge between the points Q and P. Potential energy difference. And you're talking about a small negative charge between points Q and P. So you take a negative charge at point Q and then you move it to P. So what is going to be the potential energy difference? So here, let's say take. So what is potential at Q? Potential at Q is equal to potential energy at Q is equal to potential at Q multiplied by the charge. Okay, so the charge, what are you going to have there? The charge is a negative charge, right? A small negative charge. So I will not have, say, minus Q. Okay, so what is it going to give? This is going to give me minus VQ Q dash, small charge, Q dash. And when the Q dash, the small charge, is at P, then what's the potential energy? Potential energy at P will be potential energy at P multiplied by minus Q dash again. So I'm going to get minus VP Q dash. So I'm moving it from a smaller potential to from Q to P. Okay. So what is this going to be? So this is going to give me. What is final? Final position is P. It's coming from Q. That's the potential difference, right? So final is P. So PEP minus PEQ. What is it going to give me now? So it is minus VP Q dash, then minus of minus VQ Q dash. So if I do that, then I can take Q dashed out, Q dashed out, multiplied by, it's going to be VQ minus VP. Okay, so this is what you are going to get. But what is VQ minus VP? See, VP minus VQ is positive. Here, VQ minus VP, so this must be negative. Negative into this Q dash, I'll give you a negative number. Okay, so this potential energy, so change in potential energy is going to be negative. Okay, hope this is clear to you. I want to make a note here. Okay, your book says that this is actually positive energy. That is wrong. The reason it is wrong is this. You see, you are taking the negative charge from Q to P. Even if you don't do anything, this positive charge will attract it. So it's going to go that way. Okay? So, what would the external force do in this case? It will try to restrain it from getting accelerated. So, the negative charge will be moving in this direction, but the external force will be trying to restrain it from getting accelerated. Which means that the motion is in this direction and the external force is in the opposite direction. So the work done between this point and this point will be negative by the external force. So you will have negative potential energy. So we are right and then the textbook is wrong. I just want to mention that. So the textbook says that it is positive. That is not true. Suppose the same negative charge goes from P to Q. Then yeah, that is understandable. Then in that case it will be positive. Why? Because the negative charge is going to be attracted by this. So by this positive charge. So now you need to push it that way from P to Q. So the body moves in that direction and the force is applied in the same direction. Then the external force will do positive work. Okay. But here the question is about the charge moving, the negative charge moving from Q to P. In that case, the external force will do negative work. So you get negative energy. Okay. So the calculation also reveals the same thing. So your textbook is wrong. Okay. And the same thing for the other part. So it's like having a small negative charge moving from B to A. Okay. Same thing. So if you have a negative charge here, what would it do? It would try to push it in this direction. Okay. So what would I do? I would, okay, it will push in this direction. So suppose it goes from A to B. That is the thing. Okay. So this will push it in this direction. But what would I do? I would try to restrain it from getting accelerated. Okay. So I will do negative work. Because the charge is moving from A to B automatically because it's negative charge and then you are having a negative charge here, it's going to get repelled, it will move this way, but then I'm going to restrain it from moving. So I will do negative work. So the same thing happens here. So potential energy of B minus energy of A, okay, will also be negative in this case. Okay, we want you to understand this. The textbook mentions it wrongly. That is not true. And what is the third question? Question C. Give the sign of the work done by the field in moving a small positive charge from Q to P. Now they want the sign of the work done by the field, not by the external force. Okay, the work done by the field. What are you doing? Moving the charge from Q to positive charge from Q to P. So you have a positive charge here. You are going to move it from P to Q. Okay. Anyway, this will push it that way. The charge is moving in this direction, but the force from the field is also in this direction. So work done by the field will be positive. Right? Okay. Work done by the field. Work done by the field is positive. Positive charge moving from P to Q, moves in this direction, and this will push it anyway. So positive. And what about D? Give the sign of the work done by the external agency in moving a small negative charge from B to A. Okay, so there is a small negative charge, and it's going to be moved by an external force from B to A. What's the work done? I think we already discussed that. A negative charge here, what will this do? It will try to push it in this direction. So what is the external force doing? It is taking it from B to A. So the motion is in this direction, and an external force is also acting in the direction. So the work done by the external force will be positive. Okay? So work done by the external force external, is positive. Okay. Then E, last one. Does the kinetic energy of a small negative charge increase or decrease in going from B to A? So I have a negative charge here. Suppose it has some kinetic energy. Suppose I have thrown it into the field. Okay. So it has some kinetic energy now. Now nothing else is acting, so it will go here. In this direction, try to go in this direction. What will this do? It will try to oppose that. With negative charge, this negative charge will oppose that negative charge. So the speed will decrease. So when it goes from B to A, the speed would have, by the time it reaches A from B, the speed would have decreased. Okay? So the kinetic energy will decrease. That's the answer for that question. So E is kinetic energy of the negative charge will decrease when it goes from B to A. So this is how you do this problem. Go through this problem. This will make a lot of things clear to you. Again, if you can answer all the questions, and if you understand the questions, and also why you have these answers, then a lot of things about potential energy, work done will be very clear to you. We'll do problem 2.4. Example 2.4. Let me read it out. 4 charges are arranged at the corners of a square ABCD of side D, as shown in figure. Okay? Find the work required to put together this arrangement. That's the first question. B. A charge Q0 is brought into the center E of the square, the 4 charges being held fixed at its corners. How much extra work needed to do this? Okay, so let's take a look at the picture. So you have a square A, B is 2.4, right? It's 2.4. A, B, and then C, and then D. These are the 4 corners of the square. So what is given? Side is D. Okay, so this side, this length is D. The charges are plus Q here, and then minus Q here, and plus Q here, then minus Q here. The first question is, what is the amount of work you need to do to put this arrangement together? So that's easy. I mean, I can start with A, or I can start with any charge, and then let me start with A. Okay. So what is the work I require to do to bring a plus Q to A? Nothing. Why? There is nothing in that space first. There is no field, nothing. So I am going to bring this charge. So I don't have to do work against any conservative force. So the work done to bring Q from infinity to this position is 0. So work done to put Q here is 0. Okay? Fine. Then what is the work I need to do to bring this stuff minus Q to position B? Well, now you already have Q in that place, so it will set up a field there. So there is a potential here due to Q. So what is that? The potential is actually K Q by D. That's the distance, right? K Q by D. So that's the potential at this point B due to A. And you need to multiply that with Q. Right? That's it, minus Q now. So you need to do negative work. Why? Because notice here, if you're bringing it from infinity to this position, what would this do? It will automatically attract it, right? So what is the work you will do? You will be restraining it from accelerating now. So you will do work in the opposite direction as this is getting attracted to this place. So you will do negative work. So clearly, n to minus Q is what you want to do. So negative charge, simply it's minus Q. It's going to be minus Q. So that gives you minus K Q squared by D. So you have to do negative work there. Okay. Then what about this charge? Work done to bring plus Q to this position. Well, there would be two fields, right? One field due to this one, and the second field is due to this negative charge. Okay, the negative charge will try to attract it, and this charge will try to repel it. So there will be a vector addition of those two forces. Anyway, so let's calculate the potential here. Potential due to plus Q at this position is what? It's going to be K Q by, what is the distance here? D, and this would be D squared plus D squared is equal to this, right? Maybe this is X, let's say this is X. This distance is X. So X squared is equal to D squared plus D squared, 2D squared. So X will be equal to root 2 into D. So this is going to be, this distance is going to be root 2 into D. Okay, let me do it here. So X squared is equal to D squared plus D squared. So X is equal to 2D squared square root into root 2 into D. So that is what I have taken here. That is the potential set up by this one. Now what is the potential set up by this thing? You need both of them, right? So that is going to be, let's say, K k into minus q divided by d. Because you have negative charge there. Okay, and this multiplied by this charge, that is plus q. So what I'm going to get here? I'm going to get, I can take k q squared by d out, right? K cube is kq squared, then minus kq squared by d there. I can take this out. So what I'm going to get here? So this will be equal to 1 by root 2 and minus 1. Okay? So this is what I get if I simplify it. Okay, so that is my bringing this here. Then what about the fourth charge, minus q? Like what done to bring this charge d? Well, then that's potential due to this charge, and this charge already, and then you are bringing it there. So what's the potential there? Sum of the three potentials. So first, what is the potential due to the first A? That is actually k q by this distance, that is d. Simple. And then what is the potential due to this one? So that would be plus k into minus q divided by what is this distance? Same as x, right? This distance. So that will be root 2d. And what is the potential due to this one? That would be plus k q by d. So that is the sum of these voltages. V due to A, potential due to this charge, potential due to that charge, potential due to this charge. So that's a total potential. And that potential into minus q. That's a charge. Okay. That should give me the potential, the work I need to do to bring this charge. Right? Okay. So what I get here? I'm going to get, okay, minus k q squared by d, that's the first thing, and then minus of minus plus k q squared by root 2d, and then minus k q squared by d. So you have minus, okay, I can take k q squared out, right? K q squared by d out. What am I going to get now? I got minus 2 by 1 by root 2, right? This is minus 1, this is minus 1, 1 by root 2. So 1 by root 2 minus 2. That's what I need to do. Okay, so this is the work, this is the work, this is the work, and this is the 0. So what's the total work I have to do? The total work I have to do is equal to work I have to do to bring q to A, and then work I have to do to bring minus q to B, plus the work I have to do to bring plus q to C, and then the work I have to do to bring minus q to D. So that's going to be 0 plus minus k q squared by D and plus k q squared by D into 1 by root 2 minus 1, and then plus k q squared by D into 1 by root 2 minus 2. Okay. So I can take k q squared out, k q squared by D out, and what do we get here? 1 by root 2 minus 1 plus 1 by root 2 minus 2, then minus 1. Okay? So this results in k q squared by 2 2, there are 1 by root 2 and 1 by root 2, so 2 by root 2, right? So 2 by root 2, 2, 1 by root 2, okay, then minus 1 minus 2 minus 1, so minus 4, so that should give you k q square by d into root 2 minus 4. Okay, so that's the work I need to do. So this is a positive number, this is a positive number, this is a positive number. But root 2, then minus 4, root 2 is like 1.4 positive, but minus 4, so this is negative. So effectively, you have to do negative work. Okay, you will have to do more restraining than pushing to set this up. Okay, so this is the amount of work we need to do to set this thing up. Then what is the second part? The second part is what is the work done to bring another charge Q naught to the center? Okay, to the center Q naught. Well, you can see that work done. So this is A. I want to B here. Okay, B is this. Okay, so I need to find the potential due to this, this, and this, and this. Right? I multiply by Q naught. So work done for Q naught is equal to the potential at this point into this Q naught. Potential due to all the other things. But you see, let's say this distance is y or x by 2, right? I'll call this as y. From here to here, that's y distance. What's the potential here? First one, kq by y, that's plus, and this would be minus kq by same y, because k into plus, k into minus q by y, I'll get minus q by y, simplify it, and this would be plus kq by y for c, and here again minus kq by y multiplied by q naught. What is here? Kq by y can cancel with this kq by y, this can cancel with this one, so it will be 0. So this one will be 0. So there is no net work that needs to be done to bring q naught from infinity to this position. Okay, you don't have to do any more work. You can bring it here without doing any work at all. Okay, so that's it. The energy, the work you need to do to put this square together, all the four charges at the corners of the square is this. But once you have set the square up, the extra work you need to bring q naught to this position is 0. You don't have to do any work at all, because the potential of this position is 0. So you will effectively not do any work in bringing q naught from infinity to this position. So that's what you're seeing here. So this is how you do the problem. Hope it's clear to you. In today's session with the derivation, the derivation is this: potential due to an electric dipole. So far we have discussed potential due to point charges. So now we are going to find the potential due to an electric dipole, which is nothing but two equal and opposite point charges together, separated by a small distance, right? Okay. So the way the diagram has been drawn in your book is kind of vertical, but now I will do it horizontally, because that will make the mathematics of it much clearer to you. Okay. So this is how I'm going to take the dipole. So this is a dipole. So I'm going to have say maybe this is plus q and this is minus q. Okay. So they're separated by a distance L, but I'm saying if we take this as the center of the dipole, then this would be a distance and this would be a distance, right? So 2a is a total distance. The distance of separation between the positive and the negative charges 2a. Okay. So let me take some points here. Okay, let's say let me take this point. Let's say yeah. So this is a point P. Okay. Say that point is at a distance r from the dipole and also makes an angle theta with the dipole. When you measure r, the distance r, we are measuring it from the center of the dipole r. Okay, and this is the angle theta that r makes. That way. Let us see what the potential due to this dipole at this point is given these conditions, given these things. You know the charge, the dipole, so 2a, the charge is q, and then the distance of separation is 2a, and this point is at a distance r from the center of the dipole, and then this r makes an angle theta with it. Okay. Let us try to do this now. For starters, I'll do this. I'll take the positive charge on this side and then the negative charge on this side. Maybe it will become much clearer to you as I proceed. But you can do the same thing with negative charge on the other side. But let's not worry about it. Let's say the positive, this point P is a little closer to the positive charge. So we want to find the potential at P due to the dipole. What would we do? So potential P at the, due to the dipole at the point P is equal to the potential at P due to the positive charge and also plus potential at P due to the negative charge. I need to add these two things algebraically to get the final potential at point P. So when I take a positive charge, I can't take r, I should take the distance from the positive charge to that point P, right? So I will call that distance as r1. This is r1. Okay? And this could be r2. Now I am going to express r1 and r2 in terms of r and theta, because that is the information I have. I know at what distance that point P is from the center. I don't have the information of r1, nor do I have the information of r2. All I know is that the point P is at a distance r from the center and it makes an angle theta from the center. That line. The line that joins O and P makes an angle theta. That is all I know. So I have to express r1 in terms of r and theta. R2 also in terms of r and theta. So how do I do that? Well, so one way of doing it is this. You see, if I draw a right angle triangle here, okay, what is R1? R1 is equal to this distance y, and then let's say and this distance x. Okay, so r1 is equal to y, r1 square is equal to y square plus x square. But can I express y in terms of r and theta? Yes, I can. So y is actually, we take r, that is r sine theta. Y is r sine theta. Y is r sine theta. Okay. And what is x? X is actually, you see, r cos theta is this whole distance here. R cos theta is this distance. So if I subtract this distance a from it, then I will get x. So what is x? X is actually r cos theta minus a. R cos theta, which gives me this distance, but then I want only this, so I need to subtract this that's A. R cos theta minus A. Then what is my R1 square? So R1 square is equal to y squared, which is R squared sin squared theta, plus x squared, which is R cos theta minus A the whole square. Okay. So what does it give me? It gives me R squared sin squared theta plus R squared cos squared theta plus A squared minus 2AR cos theta. Okay. So if I add these two, R squared sin squared theta plus R squared cos squared theta, I can take R squared out, then I will have sin squared theta plus cos squared theta, that is 1. So these two terms jointly gives me R squared plus A squared minus 2AR cos theta. That is my R1 squared. Okay. And what about my R2? Well, I'll do the same thing here. So R2 square can be written as, again you have a right angle triangle here, y squared plus this distance square, right? So y squared plus this distance, I call it as, the whole distance I call it as z. Okay, plus z squared. But what is y squared? We know it. Y is r sin theta. So y squared would be r squared sin squared theta plus z squared. But what is z? This z is actually this distance plus this distance. This distance plus this distance. But what is this distance? That is r cos theta, then plus a. So z is r cos theta plus a. Can I put it there? So now r squared, r2 squared, right? R2 squared is equal to r squared sin squared theta plus z squared is actually r cos theta plus a, the whole square. So that gives me r squared sin squared theta plus r squared cos squared theta plus a squared plus 2ar cos theta. Again, if I add these two, then that will give me just simply r squared. So r squared plus a squared plus 2ar cos theta. That's my r2 squared. Okay. So now I'm going to do a little more of a manipulation. I'll take r squared out from this. So now r2 squared is equal to, I'll take r squared out, and that will give me 1 plus a squared by r squared plus 2ar by r squared, that will give me 2a by r cos theta. Right? And here also r1 squared is equal to, I take r squared out, 1 plus a squared by r squared minus 2a cos theta by r. Okay, that is nice. Okay, you see, a is very small compared to, this is a dipole, right? This is a dipole. A is very small compared to this r. So I can ignore it because like r can be here. This is, we know that this distance is very, very small. So if r is much greater than a, when considering distances like pretty farther from the dipole, then a squared by r squared can be ignored because a is already small, then a squared will be even smaller. R is big, then r squared will be even bigger. So a much smaller quantity divided by a much bigger quantity will become even more negligible. Okay, so I can ignore this part in both cases. So I will say that r2 squared is equal to simply r squared into 1 plus 2a cos theta by r. That is if r is much greater than a. Likewise, r1 squared is equal to r squared into 1 minus 2a cos theta by r. Okay? Again, this is also a very small quantity. A is small, r is small, cos theta is, but I am not going to ignore it because this is much more negligible than this one. So I am ignoring it and I am just keeping this. It's a very small quantity, but I am still keeping it. But this is much smaller than this one, so I am ignoring it. Good. So this is the expression I get. Now what is R1? So R2. So R2 can be written as this. I am going to write it. Okay, what is R1 now? And so now that I have done all this here, I will take R1. What is R1? I can take square root, right? If you take square root, then I get R square will be R, then that would be 1 minus 2a cos theta by r power half. Okay? And what is R2 here? R2 is again square root of r squared is r, and you have 1 plus 2a cos theta by r whole power half. So notice now that I have expressed r1 and r2 in terms of r and theta. So the first step is done. Now I need to find this one. This is objective, right? This is objective. So now I know r1, I also r2. I have expressed r1 and r2 in terms of r and theta. So can we do it now? Okay. So this, once I get this, what does B? Vp is equal to Vp plus potential due to this at this point. What is that? It's going to be K Q by R1. Okay. Plus K minus Q by R2. Okay, so what are we going to have? So this is going to be KQ by R into 1 minus 2a cos theta by r power half. Okay, so minus kq by r into 1 plus 2a cos theta by r power half. Okay, so I can do this. This is equal to kq by r. Let me just bring it up here. 1 minus 2a cos theta by r power minus half. Oh, that makes sense to you because I'm just bringing it to numerator, so the power will become minus, right? So this will become minus kq by r into 1 plus 2a cos theta by r power minus half. Okay. You remember in the class we talked about 1 plus x, so the whole power n can be written as 1 plus nx. You remember this formula I talked about when x is very small compared to 1. You remember the approximation 1 plus x the whole power n can be written as 1 plus nx when x is much small compared to 1. So I am going to use this approximation here. When you use an approximation here, so what do we get here? Let me take this, okay. So k cube by r I can take out, right? Take out and then I can handle this separately. So this will become 1 minus 2a cos theta by r into minus r. Okay. Using this because it's a very small quantity compared to 1, so I can use this expression. Okay, so that is one part, and then minus of I get 1 plus 2a cos theta by r to minus r. Okay, so once I do that, these two will cancel and the minus minus will become plus, right? So I get this. So k cube by r into 1 plus a cos theta by r, then minus of minus 1 I can say, minus 1. Then you have this will get, so you have minus now, so minus of minus will become plus. So plus a cos theta by r. That's the expression you get. So this one and this one will cancel. Then I will have k cube into 2a cos theta by r into r squared. So I can write that as we know already, k 2a cube cos theta by r squared. But what is 2a cube? That's p, the dipole moment, right? So this can also be written as k p cos theta by r squared. So the potential at that point p is equal to this, kp cos theta by r squared. Okay. So this can also be written in a slightly different way. So you got p cos theta, right? So it is like this. So which is p? This is p. This is a p vector, right? This is a p vector. Minus q minus 2 plus the p vector. And the r vector is like this. R vector is like this. So I can take the unit vector along this r vector, and then I can express this p cos theta as a dot product of p vector and then the unit vector along the r direction. Okay, so I can write this as potential at the point P is equal to k into p vector dot unit vector along the r direction. You see, this is p vector and this is r vector. So it's going to be if I do a dot product between those two, I get p r cos theta, but I need p cos theta. So I can take just a unit vector along this direction. So I can just take a unit vector along this direction, right? So that is what I have done here. So p r vector by r squared. Okay. Hope you understand this part. So this is the final expression. Okay. So this is also equal to Vp is equal to k p cos theta by r squared. Same thing. Instead of writing it like this, I am writing it like this. So both are same. So this is what you have derived, and instead of writing p cos theta, you are writing it as p vector dot r unit vector. That is unit vector along the r direction. Okay, so you get p cos theta. Okay. P r cos theta, but the magnitude of r is 1, the unit vector along the r direction. So p cos theta by r squared. So one thing that you need to remember here is, if you talk about the electric field due to the dipole, you had an R cube in the denominator. So the E field was falling by 1 by R cube, but the voltage is falling by 1 by R square. So the electric field will fall faster as you go away from the dipole. The potential will fall a little slower than the electric field, because it is falling by 1 by R square, but E was falling by 1 by R cube. So that's the difference. Just keep that in mind. Okay. So this is the expression for a potential due to an electric dipole at any point P. You take any random point P, then you know the value of R, and if you also know the value of theta, and if you know the dipole moment, then Vp is equal to Kp cos theta by R squared. That is the expression with potential at this point. Hope it's clear to you.